little implication sign. Okay, we would not use another equal sign in between these two equations. All right, equals, let's see, 0.2 mo. All right, so we're going to solve for t. Okay, so same idea how we did here before, where we replaced m of our value. We're going to do that here. So replacing m of t with 0.2 m sub 0, it's going to equal m sub 0 e to the negative rt. And this time we're just solving for t. All right, so let's see. Well, dividing out m sub 0 again, we know these two cancel each other out. And we're left with 0.2 equals e to the negative rt. All right, we can take the natural log of both sides. I use natural log because of that e value, which means those cancel. And we're left with natural log of 0.2 equals negative rt. All right. Ooh, we have a slight problemo here, because when I divide by negative r to solve for my t value, I have negative ln 0.2 divided by r equals t. But the problem is, I don't know what r is. Or do I? Well, let's do some side work here. Remember, r is equal to natural log 2 over h, where h is our half-life, and we solved for half-life previously. Okay, so let's plug that into our calculator to find out what r is. So r is going to be natural log of 2 divided by 5.8, which is about 1195. Okay. So I'm actually going to go ahead and plug this all entirely into my problem to avoid rounding off too much. So that's going to be the natural log of 0.2 all over, replacing this value for r. Natural log of 2 over 5.8, which simplifies is actually going to be negative 5.8 ln 2 all over ln 2. So let's plug that into our calculator. Open parentheses, negative 5.8 times natural log of 0.2 divided by natural log of 2. 13. All right, so t is approximately 13.48. So what was the answer? Well, time, we're looking at how long it will take to decay. So it'll take approximately. Ooh, and what are we talking about? What is it? It is the radon. So radon 222 will take approximately 13.48. And what was time in terms of? Days. Okay. To do what? To be 20% of its original amount. And done. All right, okay, so moving on. Newton's law of cooling. 2 more pages to go. All right, so Newton's law of cooling is actually, to me, one of the very interesting uses of exponential equations, because, I don't know, I just find it rather interesting, and maybe you'll see as we go along. So the temperature of an object at time t is given by this equation, where d sub 0 is the difference between the initial temperature of the object, okay, so the starting temperature, and the surrounding temperature. Okay, so for example, if you microwaved a bag of popcorn, and I don't know, maybe let's say your bag of popcorn was, I don't know, what would the temperature of a bag of popcorn be? I'm going to make this up. 50 degrees. And the surrounding temperature in your house was 60 degrees, you would take the difference between those two, which would be 30, or negative 30. Okay, so T of S is the surrounding temperature. Okay, so that's the temperature. Maybe you're sitting in a room of, maybe like a climate-controlled room, so 75 degrees. That would be the surrounding temperature. And K is a constant. Okay, so notice that constant K has reappeared. All right, so if you're thinking of those variation problems, similar things, sometimes you might be asked to find the constant, just like we did with those variation problems. All right, so example 4. The normal body temperature is 98.6 degrees Fahrenheit. So, okay, look at this. They're so nice. They gave us K. All right, so we don't have to find that. So the constant is 0.1974, and we're going to ask that T is measured in hours. Okay, good to note that. So a body is found in a room with a constant temperature of 60 degrees Fahrenheit. Okay, interesting. So there's a body in a room, and the temperature of the room is 60 degrees Fahrenheit. So find a function that models the body temperature T hours after death. Okay, I don't know. Kind of an interesting problem to me. All right, so let's find that function. So what do we know? Well, we're going to use our given function. And we're going to fill this out. So what do we know? We know the normal body temperature is 98.6. And let's see. The room has a constant temperature of 60 degrees Fahrenheit. All right. Well, I know T sub S is supposed to be the surrounding temperature, so I can replace that with 60. That'll be 60. D sub 0, though, D sub 0 is the difference between the initial temperature of the object and the temperature that it's found in. So that's going to be 98.6 minus 60. That's the difference between the two of them. So that's going to be 38.6. All right. Okay, so we found that. What else do we need? Well, the constant we're given, which is 0.1947. So we're going to take that and plug it in. Right, so let's rewrite our equation here, or our model. 60 plus 38.6 e to the negative 0.1947 t. And there we have it. Our function that models the temperature T in terms of hours. All right, so now let's use this. So, if the temperature of the body is 70 degrees Fahrenheit, and that's what they're talking about when they found the body. So we found the body, took the temperature of the body, and the body is 70 degrees Fahrenheit. So now we're going to try to figure out how long has this person been dead. Okay, that gives us time of death. All right. I like to watch a lot of crime shows, so this is interesting to me. All right, let's see. So we want to find the time, so when the person died, when the temperature, when T of T is 70 degrees. All right, so what we're going to do is use our function, replace T of T with 70, and solve for T. All right, let's subtract 60 from both sides. That's going to be 10 equals 38.6 e to the negative 0.1947 t. I want to get e by itself so I can take the natural log of everything, because that's my normal plan. To get the variable down, I'm going to take the natural log. Let's divide by 38.6. Okay, let's go ahead and take the natural log of both sides. Reason I take the natural log is, so I can cancel, or I can simplify that. So that's going to be natural log of 10 over 38.6. All right, and now we can divide out. And we're left with our answer of negative natural log of 10 divided by 38.6 all over 0.1947 equals t. And as usual, you would never tell a friend or any other human being, I certainly hope you wouldn't, tell them the time in terms of natural logs. So we're going to go ahead and plug that into our calculator to figure out what that approximately is in hours. All right, so let's see. I'm going to put everything in parentheses since there's a lot going on. So natural log 10 divided by 38.6. Close that parenthesis one more time to close out the top. Divided by, and on the bottom, I'll just put it in parentheses for fun, why not? 0.1947 equals, 6.93. So approximately 6.94. What is my answer? So the person has been dead for approximately 6.94 hours. All right, so this is a pretty neat problem. The only thing that makes this problem, I guess, simpler is the fact that this body was found in a room with a constant temperature. Things start to get more, I guess, nitty-gritty if a body was found outside, for example, and you don't know. Maybe it was there in the evening when the temperature was lower, and if it was there in the morning when the temperature got higher. Okay, so that messes with things. Nice thing about this problem, though, is we're talking about a constant temperature of 60 degrees, so that made our problem simpler. All right, one more page to go for 4.6. Oh, actually, you know what? I think this was before I edited the document. I think that's it for... Yeah, that was it. Okay, so you have your written homework due by the end of the week. Email me if you have any questions.